I'll stop asking you this. So the problem is, even with nonlinear matter power spectrum, we still can't tell this by eye, where grad students can already do this by eye. Okay? So just want to show you all the information that's lost in the field if you do only the power spectrum. Okay, now I'm really happy that you convinced yourself that the power spectrum is not enough. So what's going on with the information that's lost in the power spectrum? So here, let's just imagine there are two types of fluctuation in our universe. One is the long wavelength mode, very large fluctuation, goes really far. And then another one is the really high frequency, small scale fluctuation, the red curve. Let's just put them on top of each other. So in a linear universe, where we call no mode coupling, if you put the observer on a hill of the long wavelength mode and another one in the valley of this blue curve, you ask them, what is the power spectrum for this small scale fluctuation? They will give you the same answer. However, in our real universe, where there's nonlinear coupling, this is what you expect. So the small wavelength mode, they actually care about the underlying over density or under density. And if you ask this to observer again, they will give you a different answer. And that is the origin of non-Gaussianity that I showed you and you found earlier yourself. So this problem is not unique to cosmology. It also exists in our society where the rich get richer and the poor gets poorer. So this problem exists both on Earth and in our universe, and we want to solve it.
The rich still don't want to solve it.
There's no rich people here, right? So let's try. So of course, our solution, at least to the one universe part of the problem, is use simulations, as we all love here. This is just one really only technical slice I have. Massive new simulation, cosmological massive neutrino simulation. So this is the models we have. We sample three parameters, A sub s. That is the initial matter power spectrum amplitude. And this is omega m, the total mass content in our universe. And this is neutrino mass sum. So we have 101 cosmological models. And we simulate them randomly scattered in this parameter space. So with this, each of the simulation, we put all our data public. We have CMB, galaxy lensing, maps, halo catalog, merger tree snapshots. We just don't have baryons. Everything else we have. So they're available at columbialensing.org, or you can just contact me if you are interested in those data. And the codes are here. Okay? So with these simulations, we are trying to help forecast or study how can we constrain neutrino mass for future surveys. And we can do that for galaxy surveys, WFIRST, Euclid, LSST, or CMB surveys, Simon's Observatory, or CMB S4.
There's one question. Are those 101 simulations, are they all the same initial phases?
Yes, that's right. So you actually can do a halo-to-halo comparison as a function parameter. I just want to show you some faces. Here are the people involved in this project. And I want to highlight the people at the top row. They're the students I work with. And on top of their head is the project they led. And I want to highlight a few of their results. Okay, so far you're already very well convinced that two-point correlation function is not enough. So what we do, we all can count. 1, 2, 3. So not surprising, let's move on to three-point correlation function. So very similar to two-point correlation function, instead of dropping rulers, now you drop triangles. And ask again, how likely are you going to find galaxies at each angle of this triangle as a function of the size of triangle and the shape of it? So there, I want to show you two examples. One triangle is the equilateral shape. So there's only one free parameter here. It's just the size of the edge, or size of this triangle. So on top, I'm showing you the equilateral weak lensing bispectrum, which is in the Fourier space as a function of scale. So I'm also showing you two redshift. This is redshift 1, redshift 2. So here you already can see there's some evolution of the bispectrum. And the solid curve is massless neutrino, and the dash curve is massive neutrino. So you see some suppression already. Yes?
Very nice question. Can you tell us how do you define the bispectrum? Bispectrum of what?
A bispectrum of weak lensing. So here we are not doing.
Effect of neutrinos, or because in reality you could have some intrinsic non-Gaussianity going on as well. I'm not sure what's the context of non-Gaussianity that you're talking now. Can you just tell us?
Sorry.
It's like a lensing, and then you also add massive neutrino for each of them, right? But
That's right.
linearly or non-linearly?
Linear, non-linearly. All we're talking about is non-linear right now. So everything is non-linear because we use embodied simulation. So non-linearity is automatically captured in all the simulations.
Yeah, but you already have seen that in the power spectrum, they are up to 10%. So I'm confused that in the 3-point function, the non-linearity could be even important.
That's right, that's right.
So then why you care about?
Bispectrum?
Yeah, non-linearity in the bispectrum. It's already too much.
So if everything is linear, then bispectrum should be 0. We should not see anything in bispectrum. And bispectrum should contain information that's not captured in the power spectrum.
So what is bispectrum? It's a 3-point.
That is the 3-point function. So bispectrum is a Fourier transform of a 3-point correlation function, because it's just simpler to calculate.
You fix the shape of the triangle and you Fourier transform according to the this of that.
Yeah. Yeah.
So
you can.
The source of non-Gaussianity is non-linearity in neutrinos. Is that right?
Neutrinos are linear mostly because they are they don't really cluster. However, they have a back reaction to the matter power spectrum or matter clustering, and that translates to the change also in their non-Gaussian features. Yeah. Okay. So there are two things. One is we do see suppression of bispectrum as well, or 3-point correlation function, or also we also see evolution in redshift space. So this is the equilateral shape. If we go to squeeze limit, where you have 2 really long legs and 1 small legs, and here you are instead looking at how small scale fluctuations are responding to the large scale fluctuation, just like the example I showed you. So first thing you notice that there's also redshift evolution, but the shape of it, dependency, is changed than the other triangle. That means different triangle will carry different information. And also we are trying to combine this and then compare them to the power spectrum and see how much more information we can get out by adding the bispectrum information. Please.
So I'm sorry if you mentioned this, but in your simulations, do you treat the neutrinos as a separate particle species, or do you just sort of modulate the initial density field?
So yeah, that's some technical detail. We do not use neutrinos as a separate particle species. We treat them as a linear component, because but then we evolve neutrino each step using the nonlinear matter power spectrum we measure from the simulation. Yeah. So that's the benefit of it is it's really fast and there's no shot noise. But then the neutrino power spectrum is a little off, but that's something you can never imagine to measure anytime soon. So we don't really care about that. The total matter power spectrum is entirely correct. Okay, I want to show you quickly the result using 3-point correlation function. This is a work led by Will Colton. He was a student at Princeton, now a postdoc at Cambridge. Here the parameter constraints 95% contour. So here are the 3 parameters I mentioned. Let's just focus, say, one part of the plot. So using the power spectrum, this is what you expect. The blue contour, and using bispectrum, it's the black contour. So you can see that using bispectrum, you already can get comparable constraint as the power spectrum. And then when you combine them jointly, you get improvement about 30 to 40% on the neutrino mass.
Which triangles are you using here?
All triangles, yes. So that is because they have somewhat different degeneracy in our parameter space. By combining them, you break the degeneracy and have a better constraint. Okay?
Was this assuming a CMB prior?
No, we did not assume. That's why the constraint is so bad right now. If you combine them, it will be much better. Yes. Okay, so yeah, this is very encouraging. Let's move on and do 4-point correlation function. Yes?
Sorry, so you said like assuming L is still like noise, is this with photometric pressures or?
Yes. So LSC noise mostly coming as shape noise because weak lensing signal is very small compared to the shape, intrinsic shape of the galaxies. So we model them using what we expect from LSSD, which is like typically 10 times as large as the lensing signal. And also DNDZ, we assume some distribution of their galaxies and then put in our simulation. Yeah. Okay, 4-point correlation function. Well, before moving on to 4-point, one thing I want to mention is people actually did 3-point correlation function on data. It's not easy because there are so many triangles you have to measure. Computationally, it's difficult, and modeling is not easy neither. But people actually did this with weak lensing survey, CFHE lens. And you can see that 2-point